So we saw that when we have two conductors with certain charges, post connection, the charges will redistribute till a point of what? Equipotential, right? Now the question is, what happens to the energy per se? See, when we are talking about redistribution of charges, means what? We have movement of charges. Movement of charges is nothing but your current. For example, in your device, we have current flowing, right? So what is one thing that is happening inevitably? Yes, it's heating up. The device is heating up, right? Whatever device you guys are using as of now, it's hotter than, say, some minutes back. So here too, when there is redistribution of charges, there is loss of energy. And here we are trying to figure out loss of energy, how much in terms of your initial and final voltage or capacitance of the capacitor and so on and so forth. Okay, yes. So your final expression will be expressed in terms of, say, C1, C2, V1 and V2. Now, first thing is, let's have a look at what is the energy of system initially. So U initial is equal to U1 plus U2. So there are many formulas, many expressions for this, but obviously we'll make use of this. Reason being, we want to express in terms of, the final expression has to be in terms of C1 and V1, C2 and V2. Okay, yes. This is square. Now, post connection. What do we have? We know that voltage on A will be equal to voltage on B, which will be equal to V, total voltage V. Now, the question is, what happens to the energy? Again, we are trying to talk about energy of the system. So energy of the system, this is, actually I want to use a different color. Post connection. So what's happening, right? So say this, we'll call it as UF. This 2 will be equal to half C1 V square plus half C2 V square. Very simple. But of course, we have to express in terms of the initial conditions. For that, what will we do? Well, I can substitute for V. Let me do that. Into V square, right? I'm taking V square and half common. So we're going to substitute V as, we know this. It's nothing but C1 V1 plus C2 V2. This entire expression divided with C1 plus C2. Then difference in potential is final minus initial. Okay, sorry, I have to substitute it over here. That we can do it here itself. Sorry, initial minus final, because initially the energy is more than the final one. So initial is what? Initially we have this to be half C1 V1 square plus half C2 V2 square minus, this will be half C1 plus C2, and this would be C1 V1 plus C2 V2 the whole square, entire thing divided with C1 plus C2 whole square. So this and this will get cancelled. So this is 1 this entire thing is 1 the powers, that is, so 2 minus 1. That's the right way to put it across. Then half is common everywhere. What else is common? Nothing else. So I'll take half out. And we have C1 V1 square plus C2 V2 square. And then we have, oh yeah, sorry, we can't do that. Minus, I was thinking of expanding this without, that will not happen. V1 plus C2 V2 whole square divided with C1 plus C2. So we need to do a bit of math over here. So half is common, then I'll take C1 plus C2 also out. Okay, so let me edit neat. 1 by 2 times of C1 plus C2, brackets open. So when I take the LCM, this will be using redistributive property. So this will be C1 square V1 square plus C1 C2 V2 square plus C2 square V2 square plus C1 C2 V1. Okay, please don't get confused. I kind of did the redistribution in my head. Minus of C1 V1 plus C2 V2 the whole square. Yeah, you guys, you do the math, you'll get the same expression. So this is A minus B the whole square. When I expand it, this term and this term will get cancelled. And we'll end up with 1 by 2 C1 plus C2 times, in the numerator, what do we have? So we'll end up with C1 C2 V2 square plus, oh, not, no, it is square, right? There is a square. Plus C1 C2 V1 square. And here we'll left out with 2 C1 C2 V1 V2. Again, when you expand it, things will get cancelled. So you don't have to show every possible step. It's of no use. Right? No one will ask you this detailed answer. I mean, detailed steps, that is. So finally, what do we have? We have C1, C2 common. So the final expression is C1, C2 divided by 2 C1 plus C2. And in the numerator, we have V2 square plus V1 square minus 2 V1 V2. This is in the form of A minus B the whole square. So C1 C2 V2 minus V1 the whole square divided by 2 C1 plus C2. So that's your final expression. So what can we tell? Clearly, there is reduction of energy by this factor. Okay, guys. So let me take a second. Right, one last go. So we know that charges on a conductor, it will be at equilibrium. If you connect two charges which has unequal distribution or at unequal, not distribution, unequal potential, what happens? They will move till a point of equal potential. Movement means current. Current, leads to, yes, heat. So there is loss of energy. And that loss of energy we are trying to figure out in terms of the initial voltage and the capacitance of the capacitors or devices or materials. So we are getting an expression for the initial system's energy and final system's energy. And the difference between them will give us the answer. That's it, as simple as that. Here the math is a bit lengthy, if not nothing else. It's quite simple.